Hello everyone, my name is Maxwell Hoem, and this is my Physics 2 Lab 3 slides for Physics 2212 here at Georgia Tech. So a bit of an introduction to this experiment. So in this lab, we will be using a magnetometer and a bar magnet to calculate both the equation for the magnetic field of that magnet and the dipole moment of the aforementioned magnet. We will do this using a few fundamental physics principles. Firstly, we will use the magnetic field of a magnetic dipole formula, as shown in the top right. And then we'll use the properties of logarithms to approximate exponential equations, as shown in the bottom. Part 1, the process. So there's a bit of a setup to this experiment. Firstly, you will need to gather materials, including a bar magnet, a magnetometer, either a real one or one on your phone, a meter stick, a ruler, or a few pieces of tape, and the Excel spreadsheet associated with this lab, mine of which will be included in the description of this video. Next, you must find a suitable location. Said and done, especially here at Georgia Tech. Basically, what you need to do is you need to find a place near untainted with the electricity. Next, you must line up the magnetometer with true north, or rotate it until the Bx component of your magnetometer is equal to 0, so that you don't have to worry about the magnetic field of the Earth. Next, the setup. What you need to do is you need to take the ruler and the actual magnet, and then you will set them up perpendicular to your phone pointing true north, so that you can make sure that you have everything lined up. Next, you must find the location of the magnetometer in the phone, which you can do by moving your phone directly up and down until the By component of your magnetometer is at a minimum value. Next, the measurements. So you must measure the horizontal distance at which the X component of the magnetic field is equal to each of the rows in the spreadsheet 3 times and enter them into their appropriate spots. So a few statements that describes what I observed. So when the magnetometer is far away from the magnet, it does measure a near zero magnetic field in the X direction, as magnetism decreases or scales inversely proportionally based on the distance. Next, as the magnetometer moves closer to the magnet, the measured X component does not decrease. And then the position of the magnetometer, it does have an effect on the measured X component of the magnetic field. And finally, as the magnetometer moves closer to the magnet, the measured X component of the magnetic field does increase. Okay, first part of my results. So just to go through this, for my average distances at a distance of 2.07 times 10 to the negative 1 meters, the magnetic field, Bx, or the X component of the magnetic field, had an average magnitude of 2.0 times 10 to the negative fifth t. And then these are the rest of my results, as you can see, as the averages. If you want to get a little bit of a more in-depth look at all of my results, I will include my spreadsheet in the description. You can take a look at that. Next, the natural log graph of the data. So what we can do is to actually calculate each of the unknown components of our bar magnet, as we do not know the dipole moment of it. What we can do is we can take the logarithm of the X component of the magnetic field and the logarithm of the distances x, and we can plot those points on a graph, and this will make it linear. And then with a little bit of math magic, each of these coefficients for m and b, or the slope and the y-intercept, the slope will be the actual n component as seen here in this top left equation, which was a bit of a simpler formula for the magnetic field of a bar magnet. And that n component is how quickly it scales off as the distance increases. And as you can see, my n component is equal to 2.6922, which is actually pretty close to how the actual formula is. So I was pretty proud of that. And then k, which is a bunch of different constants, including the dipole moment of the magnet, is going to be the y-intercept, which I calculated to be negative 15.1. Then with a little bit more math magic and plugging in formulas and that kind of stuff, we can calculate the dipole moment, as I did, to be approximately 1.38395 for my magnet. Next, we calculated the off-axis magnetic field, where we took the magnetometer and we moved it a distance deeper, or the perpendicular distance where the magnitude of B net equals to 100 mu t, away both horizontally and vertically, so that the distance away from the bar magnet was at a 45-degree angle at a distance at a distance of square root of 2 times d per away. I use this to calculate the off-axis magnetic force of the bar magnet, where my results were actually distance d perp equal to 0.6122 meters, and my magnitude of my magnetic field was equal to 3.49 times 10 to the negative 15. So a couple what ifs to take into account if we were to do this experiment a different way. So what if you hadn't oriented your experiment to compensate for magnetic north and instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? So if you actually didn't know how many degrees away from magnetic north or magnetic south, or you don't have some sort of catalog that would be able to tell you, you actually would just have a completely incorrect n and k values, as if you didn't take it into account, your n and k values would have either increased or decreased based on the orientation of the meter stick with respect to magnetic north. But if you had taken that into account, which would have made it more complicated, you would have been able to get the same answers, albeit much more complicatedly. So second what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? So if you stuck them both end to end, obviously the measurements for the distance for each of the B net mag values, the distance would have greatly increased, thereby increasing the value of k, although this would not have increased the value of n, as it would have scaled off at the same rate, albeit it would have started at a much higher value. So here's the coding model, which we actually took, and we went and we did some coding and some cool stuff like that. using the dipole moment of our magnet, and then we created a coding model so that we could plot arrows anywhere on the graph, and it would show us the actual magnetic field at that point. So I made 7 arrows actually. I made two on-axis arrows, which were twice as strong as the 4 perpendicular arrows to the magnet's magnetic field or dipole moment. And then I did one in the top right at 45 degrees, referencing this off-axis arrows that we plotted. Yeah, here's my coding model link. You are more than welcome to look at it and take a crack at it yourself. I really enjoyed it because I really enjoy doing computer models of things. I always think it's very cool to use computers to solve your problems. But yeah, so a couple conclusions. I really enjoyed this because I always enjoy labs. They're always great to see that what we're learning in class actually applies to the real world. But yeah, I hope you guys enjoyed my lab. I enjoyed doing this, and I hope you guys have a good day.